Okay. Welcome back. This is a lecture on part of a lecture on short braced axially loaded reinforced concrete columns. So in part one we looked at the basics of braced unbraced columns, and in this video, this is just like the first introduction into part two, short braced axially loaded columns. 2.1 development. So development of the theory of design of concrete columns. So the design of such columns is very straightforward. The ultimate force is the sum of the stress times the areas of the steel and the concrete. So N crush N N. Oh yeah. So basically, in this type, as I've done another video on this as well, the concrete and the steel fail in compression without buckling. So crushing the concrete yielded the steel without Euler buckling. So NUZ equals 0.67 FCU divided by gamma material. AC times the area of concrete plus the Fy of the reinforcement steel divided by the gamma material for the reinforcement times the area of the steel, and remember that 0.67 it said that is not a material safety factor. That's another factor. So yeah, for concrete the gamma material concrete is 1.5, and for steel gamma material steel is 1.05. That's reinforcement steel, and it says this is due to change back shortly to 1.15. So therefore we have we plug in those material gamma, those safety factors for steel and concrete, and you get NUZ equals 0.45 FCU AC plus 0.95 FY ASC. Okay, so that's basically just so you got compression of the concrete and compression resistance of the steel. Because this relies on a perfect actual load, which is virtually impossible to achieve in practice, a small allowance for an eccentricity of approximately 0.05 H is made to give N ultimate resistance is 0.4 FCU AC plus 0.8 FY ASC. So that's 0.4 times the cube strength of the concrete, or the grade of the concrete, times the area of the concrete, plus 0.8 FY ASC. For a rectangular section, this is equal to N ultimate equals 0.4 FCU BH plus ASC brackets 0.8 FY minus 0.5 FCU. So basically so let's say if that is this, the first equation is equation 1, then it's 2, 3, 4. So in equation 4, area of concrete is obviously B times H, and what he's also done is, as it says in that last paragraph, notice that we have effectively reduced the stress in the steel to account for the concrete that isn't present, but which we have allowed for in the first term. We will do this again. So because the area of concrete AC is actually the area of the column minus the area of steel. So he's got N ultimate is 0.4 FCU BH, which is the area of steel, plus then it was 0.4 FCU BH, which is BH is the area of concrete, plus ASC is the area of steel. So so it would be ASC. What if you work out this equation, it will be NUZ equals 0.4 FCU BH plus ASC 0.8 FY minus ASC 0.4 FCU. So you take away the area of steel from the BH, from the area of concrete. So it's just the same, except minus the FCU area of steel. Notice that we have effectively reduced the stress in the steel to account for the concrete that isn't present, but which we've allowed for in the first term. We will do this again. Okay, so that I think hopefully everyone can understand that is fairly straightforward. This is like, I've done another video on short braced axially loaded reinforced concrete column, a complete video, but I'm just going over it again because this is an introduction to reinforced concrete column design, so we need to know the basics again, so I'm just going over it easily before we get on to the next step is obviously a short braced column with moments as well, and basically so now let's look at example 2.2. so when you have a braced column, basically it means, as I said before, that the shear walls or lift cores or say steel diagonal bracing, they provide resistance to the lateral forces on the building, so that any lateral, like say for example the wind load on the building is transferred from the face of the building, the elevation, via the plate action of the slab to the shear walls or the lateral bracing system. The columns aren't used to provide moment resistance to the lateral loads, so there's no moments on the this is the most simple case. This is short column, so it fails in crushing. There's no like deflection. We'll come on to slender columns in the next video, but in another video. So the problem here is we've got a short braced column, 300mm square, and supports 1700 kilonewtons at the ultimate limit state. The characteristic material strength are Fy, steel reinforcement strength, equals 400 newtons per millimeter squared, and FCU equals 30 newtons per millimeter squared. Design the steel for the column. So that's problem number one. Let's go to a solution. I've already worked this out. It's very simple anyway. I'm just showing to, like, someone who's just starting off. The example problem, solution by R.J. Nash. A short braced column is 300mm squared and supports 1700 kilonewtons at the ultimate limit state. The characteristic material strengths are Fy, which is the yield stress of the steel, is 400 newtons per millimeter squared, and FCU, crushing strength of the concrete, is 30 newtons per millimeter squared. Design the steel for the column. So we use the equation. I just called it equation 4. We use equation, this one here. We use equation 4. So NUZ equals 0.4 FCU BH plus ASC brackets 0.8 FY minus 0.4 FCU. AC equals BH, and so now we've got actual value. It's 300 by 300. So 300 times 300 is 3 times 3 times 100 times 100, which is 9 times 10,000, so 90,000. Fy equals 400 newton per millimeter squared, and FCU equals 30 newtons per millimeter squared. N ultimate equals 1700 kilonewtons, so that's 1,700,000 newtons, or 1700,000 newtons. The load so this is very important because this is the load that the column needs to withstand. I think that's quite a large load. Remember, NUZ is the ultimate crushing resistance strength, i.e. the concrete in the column fails by crushing only, and the steel by yielding and compression, not by buckling failure. So this is not a Euler buckling load. So it's quite straightforward. That was equation 4. I just call that equation 4. Let's plug the values into equation 4. We got 1700,000, so it's 0.4 times, in this case 30, area BH is 90,000, plus ASC required, 0.8 times Fy is 400, minus 0.4 times 30 is 1700,000 minus 1,080,000 plus ASC required 0.4 times 400 is 320. 0.4 times 30 is 12.